Let me start asking, who was in the tutorial about dynamic time warping yesterday? Just raise their hands. Okay, I really recommend that. The slides are online. Well, okay. My talk is about dynamic time warping, which is a largely used measure to compare time series objects. And it works like this. If I have two time series, like the blue one and the red one here, they're quite similar, but they have a shift regarding the time axis. So the dynamic time warping tries to align those time series using a dynamic programming algorithm. It uses a cumulative cost matrix like this one. The hot colors here, the red, it means high values, and the blue, the cold colors mean low values in this cumulative cost matrix. I'm sorry. And dynamic time warping tries to find the optimal alignment path, which starts in this point, bottom left in my case, and finishes in this cell here, top right. Yes, top right. And then it finds an alignment like this. It's different from Euclidean distance, which finds an alignment that is linear, point by point. What is important here for my presentation is this restriction that dynamic time warping needs to start in the first pair of observations, so we need to match them, and then it finishes in the last pair of observations. We need to match them. What happens in the middle, it depends on the algorithm. However, let me explain this data set, Gunpoint. It's a bit famous data set. We have some time series here obtained by tracking the hand of an actress, pointing the finger or a gun to someone. And it was obtained using metronome, beeping it 5 seconds, and it was like beep, and then you get the gun, and then beep again, and you put the gun back. We have a lot of different time series like this. It's really useful to test some algorithms, but at the same time, it's probably not sufficient, because this is a case that is really easy to obtain the data, to segment the data, but in a real scenario, it's not like this. For instance, the girl could be talk to someone before, get the gun, or use the cell phone. So it's not easy to have something like this plateau here, and then the event, and then the plateau again. The most common thing is like this one. There is a movement before that we say it's a prefix of the event, and there is a suffix that is the movement after the put back the gun or the finger here in the same position. And at the same time, I can't believe that if she's pointing a gun to someone, I don't think she would do something like, okay, give me all your money. Oh, no, forgot about it, and put it back. So we have something like this, that we don't have any suffix at all. So to match this time series to something like this, it's something that we can do with dynamic time warping. And this is a problem. Actually, we can do, but we have this problem there. Consider this example. It was in the tutorial yesterday. This is Australian sign language. I don't remember exactly the word, but it's tracking the hand. It's for the same word, so you can see that the time series are quite similar, except for these points at the beginning. We have this slope here, and because of the endpoint constraint of dynamic time warping, which requires the matching of all the observations, and mainly the first one, this is a problem. It's accumulating 7% of the distance between those time series. I mean, now if the distance between the time series are 10, I don't remember exactly, so 7 is just for this region here. What is a problem, right? So our solution is to avoid this match in the beginning of the time series or in the end of the time series, avoiding the not informative prefix and suffix. And sometimes I just use the word endpoints for both. Okay? So basically, this is what we did. The original endpoint constraint of time series says that the matching is made for the entire length of the time series, both objects, x and y. Then it starts in 1, 1. It means the first observation of each object. And it finishes in n, m, being n and m the length of the time series. So basically, when you have the cumulative cost matrix, the DTW needs to start here in the red point and finish in the red point. We modify it relaxing this endpoint constraint, allowing the dynamic time warp to start in any place here on the gray or red cells, and finish again in any of the gray or the red cells. I won't stop here so long, but basically I want this slide to say that we just modified the initial condition of the dynamic programming algorithm. This first part means that I'm starting all these cells with zeros. It means that I have no cost for match then here. And also, I look for my answer not here in the matrix, but in any region here. Just it. It's a really simple modification. In the algorithm, it's just one line. I should put the algorithm here, but it's a really simple modification. There are some stuff that are quite related, but actually for another purpose. So this open-end dynamic time warping, it was proposed for the case that I have really nicely segmented time series in my training set, and I want to classify time series that I know the beginning of them, but probably I don't know the end. It's the case of the pointing and stay pointing. The problem is that they propose it to open the whole end. It means that the whole last column with the gray cells in my previous example. And then someone modified it to open the end and the beginning. There are some problems with this kind of approach. First of all, it's not symmetric, so I can have some results that are not desirable. For instance, I tried to cluster those objects here using the same algorithm, open beginning and end dynamic time warping, but showing the examples in a different order to the clustering algorithm. And I have a completely different clustering. It's kind of, I don't want to have this kind of behavior, right? And also, I have a pathological example here, but it may happen because it's opening the whole beginning and the whole end of the time series. So I can have some alignments like this, in which all the observations here in the red time series is matching only one observation here in this time series. And it's also something that we don't want to have. All right, I have this sanity check. I tried the same clustering with this time series here using dynamic time warping. I can have a really good result here. It's kind of weird. The good one will be group the blue one and then the red one. It's better using OBE, the open beginning and end dynamic time warping, but with our proposal, we can perfectly cluster all the objects. Well, let me stop here and tell some notation for. I didn't talk about the warping window. Basically, the warping window is something that will limit the distance in the time axis for matching observations. In the matrix point of view, it's basically that the optimal alignment path should be something close to the main diagonal of the matrix. When I'm using this, I use this letter C here, all right? And psi, I forgot to say that. Psi is for my algorithm that's prefix and suffix invariant dynamic time warping. Okay. Our first experiment was using some data sets that we know exactly that we know that they are exactly segmented. The time series are good there. They don't have suffix and prefix, something like the gunpoint, okay? And then I started to add some random noise before and after it, like prefix and suffix. And I tried to classify them using the regular dynamic time warping and PC dynamic time warping. The accuracy is worse when I add more and more and more random data as suffix and prefix, but it increases slowly when I'm using PC dynamic time warping. This is for a cricket dataset, a specific dataset, but this is the general behavior. Given that, we made some case studies. For this, we got some datasets in streaming data, and we segmented using a sliding window, okay? And then we applied some dictionaries to make the training data. If you don't know the dictionaries, I recommend the paper Time Series Classification Under More Realistic Assumptions by Professor Eamon Keogh. It's basically, you just get the best short number of objects for the training data, okay? I have this parameter R, there is the relaxing factor. It means the number of cells that are relaxed in the beginning and the end of the time series. And I'm learning this parameter using the training data. And because I'm not concerned about to find the best warping window, I fixed this in 10% of the length of the time series. And then I have some data sets from real scenarios. The first one is the motor current. Okay, I forgot to say something. Because I'm using streaming and sliding windows to segment it, I assumed that I don't know the best size of this window, okay? So I varied this in my experiments. And I found a range of sizes empirically using DTW, the regular one. Okay, so for this case, this is probably the best case for my algorithm. Independent of the time series length or the window length, I got the best results with a large margin. Okay, so this is accuracy per, and this is the length of the time series. In some cases, like in the second one, the amiable robot surface that is a dog-like robot walking on cement or carpet or something, the accuracy is better for my algorithm in most of cases. And sometimes I have the accuracy that is exactly the same than the regular dynamic time warping. It means that when I was learning the parameter R, I learned the value 0. And it's exactly dynamic time warping. So the regular dynamic time warping is a special case of my algorithm. This is the worst case for my algorithm, that the results are kind of mixed. I'm not doing worse, but I'm not doing better. Basically, I think it's saying that for this data set, it's using the same robot-like, but I'm trying to classify the activity like running or playing soccer. For this data set, I think the prefix and suffix are not that interesting to look to. But even so, the results of my algorithm is similar to dynamic time warping. I have some more results. I think it's better to check in the paper the detailed results. I have for gesture data and the sign language as I use it first. And also I classify human activities using smartphone, accelerometers, and etc. The important is that in most of cases, CDTW is performing better. And I have this is not in the paper, but this summarizes the results. For this table, I got the best result of dynamic time warping, looking directly to the accuracy obtained by the test data and get the best result. So I'm kind of cheating because I'm assuming that I already know the best length of the time series, okay? And I'm not doing this for the PC dynamic time warping. I'm trying to learn it in the training data as well. Even so, I get the best results in virtually all the, cases here. Only in this case, I have something like a similar accuracy. Okay, and using all my results, I performed a hypothesis test, and it's saying that, okay, CDTW is significantly better than dynamic time warping. And okay, given that, I have the concern that, okay, dynamic time warping is a bit slow. unless you have, you can use some techniques like lower bounding. For this, again, I recommend the slides of the yesterday's tutorial by Professor Nguyen here. But I have in the paper the demonstration of a slight modification of LBQ to adapt it to my proposal. It's a really subtle modification, and I show that this lower bound function is as tight as the LBQ for dynamic time warping. Because my time is running here, let me conclude. So the suffix and prefix are present, mainly in data stream, because the segmentation is a really hard task. And dynamic time warping can deal with this. And I showed that I can obtain better accuracies than the regular dynamic time warping. I can tightly lower bound it, so it can be fast. But I still need to improve how to learn the parameter R. I'm using the training data. It's a naive approach. And in general, I'm getting good results. But I can do better. And also, I want to apply it in different mining tasks like clustering or even motif discovery. And that's it. Thank you.
Well, first, I do want to say that I really did actually enjoy the tutorial yesterday, and I think that there was a lot of detail that I don't think were able to cover. I'm just wondering if you can share the slides again, like provide people a link right now.
Yes, I don't know, Nguyen.
Or is that going to be available?
Yeah, so for the entire workshop, we are collecting these slides from the tutorials, keynote speakers, as well as from the authors. So it'll be available in our website of the workshop.
All right, thank you.
Any other questions?
Actually, I was wondering if you could share some use cases of types of analyses that you've used dynamic time warping for, and why it might be something worth learning.
Excuse me, I can hear it's kind of...
Oh, I was just curious about some use cases for dynamic time warping, if you had any suggestions. Or your modified version of it.
I don't know if I get it. Are you talking about the use cases for dynamic time warping, and if?
What kind of analysis would I use it for? What data?
Yes, I have the data on the website. The website is in the paper. Okay. Most of them are freely available. Okay. Some you need to ask the authors. And also, there are some different things that I made, like some are segmented already, and then I made some strings, and I have a code there to segment just using a sliding window. That is basically, I'm sliding the window, get a lot of time series, and creating the dictionary using simple ring. That is an algorithm. I also have it there. I don't know if I answered your question.
That's fine. Thank you.
Okay,
So is there any other question from the audience? Okay.
Just curious, so empirically you showed this proposed algorithm works really well. So is there any way that you ever thought about doing some theoretical analysis in terms of explaining or giving some bound of how the algorithm performs?
No, actually, I can't answer this question. I don't have an idea. I really made something really empirical for now. Actually, I kind of followed some intuitions that it. No, I don't have anything theoretical to say that it's better if I have a bound of error here or not, or something like this. And I need to think about it. Oh.
Thank you for your presentation. Just curiosity too. You defined your R value based on
Yeah.
this data, yeah? And you said that you have some ideas for future work on changing it. Can you give us any insight of how would you do that differently?
Yeah, actually, one thing that I did, the results here are obtained using the dictionary that is a small training set, and then I have some time series that are not the dictionary, so I use this as a validation, and I use this data set to like a training. But the problem is this is too small, and I tried to use several different ways. The results are kind of the same right now, but I think that the R is not something the same R for the whole data set, probably for each pair. So for this, I still don't know how to do. But I think this is the point. For each pair of time series, I may have different value for this parameter, and I need to know how to do that. I don't know.
Thank you, Diego.